for the 2018 chemical reactivity for level 2 chemistry. So question 2, the contact process is used industrially in the manufacture of sulfuric acid. One step in this process is the oxidation of sulfur dioxide SO2 to sulfur trioxide SO3. So question A, we have write the equilibrium constant expression for this reaction. So in terms of writing the equilibrium constant, we know that's equal to the concentration of the products over the concentration of the reactants. However, we need to remember that the amount of moles needs to be raised to a power in the equilibrium constant equation. So Kc equals to concentration of products over concentration of reactants. And remember, you have to use your square brackets, okay? Square brackets for your Kc. So for Kc, in this case, we have 2 moles of SO2 reacts with 1 mole of O2, and that gives us 2 moles of SO3. So in this case, our equilibrium constant would be concentration of SO3 to the power of 2, because we have 2 moles of SO3, and that's over concentration of SO2 to the power of 2 multiplied by concentration of O2. And that's our equilibrium expression. Question B. Calculate the equilibrium constant Kc for this reaction at 600 degrees Celsius using the following concentrations. So SO2, concentration of SO2 is 0.1 moles per liter, the concentration of O2 is 0.2 moles per liter, and the concentration of SO3 is 0.0930 mole per liter. So to calculate to calculate the equilibrium constant, all we need to do is just plug in the concentrations for each of these species, and we can find the equilibrium constant because we have our equilibrium expression. So therefore, our Kc equals to the concentration of SO3 squared, 0.0930 squared, divided by concentration of SO2 squared, was 0.100 squared, multiplied by concentration of O2, which is 0.200. And all we need to do is just plug these numbers into our calculator. So alright, so we should be getting the value of Kc should be coming out to be 4.3245, and then we're going to round this one down to 3SF, so 4.32. So our equilibrium constant is 4.32 in this case. Alright, so in terms of the grades for these questions, so for question A, writing the correct equilibrium constant will get you an achieved. For question B, if you find the correct equilibrium constant, you will get a achieved. And in terms of getting question II, so explain what the size of the Kc value indicates about the extent of the reaction at equilibrium. So in this case, we can see that Kc is bigger than 1, which means that the products are favored, or in other words, the forward reaction is favored. So the concentration of the products is greater than concentration of the reactants. So in this case, if we want to look at it mathematically, we know that the Kc is equal to the concentration of products over the concentration of reactants. Since Kc is bigger than 1, that means the numerator has to be bigger. So therefore, that means the concentration of the product has to be bigger. So in this case, we can just say that concentration of the products will be greater than the concentration of the reactants. And that's all we really need to say for statements. We just say the concentration of the products will be greater than the concentration of the reactants at equilibrium. And you can say this is because Kc is bigger. Kc is bigger than 1. And you can actually get a merit question. You can get a correct calculation. And you can link that Kc is bigger than 1. Therefore, there's going to be a more concentration of products than concentration of reactants. So linking both of those ideas here will get you a merit. Alright, question C. Explain using equilibrium principles why it is important for an industrial plant to continue to remove the sulfur trioxide gas SO3 as it is produced. So as you can see here, SO3 gas is a product. So if we don't do anything to this reaction, after we initiate the reaction, it's going to take some time for the reaction, and then it will be the certain Kc value will be reached, so equilibrium will be established, and then the equilibrium will still be there'll still be reactants turned into products and products turned into reactants. However, there's no more net change, which means that the overall net change, there's no more net change, which means the reaction effectively stops. However, if we keep taking SO3 away from the away from the if we keep taking SO3 away from the equilibrium, then the equilibrium will shift in the direction to reduce the change, which means that more SO2 and O2 will react to replace some of the lost SO3. So this ensures that we can keep getting more and more SO3, sulfur trioxide gas, produced. So if we keep taking SO3 away, that means more SO3 will be produced because equilibrium will shift to favor the products. The forward reaction will be favored, and therefore we will get more SO3 gas, which is beneficial for the industrial plant because we do want to have more SO3 gas produced. So basically, just linking those points together. So we can say that when SO3 gas is removed, equilibrium will shift in the direction to reduce the change. Since the concentration of SO3 decreases, because we're removing SO3, so we're removing SO3. So to maintain the Kc value, equilibrium will shift to favor the products, or in other words, the forward reaction is favored. So forward reaction is favored. So we can say that more SO2 and O2 will react to form SO3 gas. So you can say this is to replace some of the lost SO3 gas. This is to replace some of the removed SO3 gas. Alright, so you can say this is beneficial for the industrial plant because SO3 gas can continuously be produced if we keep removing it. Because SO3 gas can be continuously produced as we remove SO3 gas from the equilibrium. Hence the amount of SO3 that the plant is getting increases. Hence the amount, or we can say the concentration amount of SO3 gas produced increases. And that's really all we need to say for this question, okay? So, alright, so question C and D are actually linked, so we'll do question D. So, predict using equilibrium principles the effect on the concentration of sulfur trioxide gas, SO3, of carrying out the reaction in a larger reaction vessel. So, when we have a larger reaction vessel, it's actually having a larger volume, okay? So, there's more space for the gas particles. So, in this case, because there's more space, you can think of it as equilibrium will shift in the direction to produce more gas particles in order to fill up this extra space. Okay, that's the way you can think of it. So there's more space now, so the equilibrium will shift so that more gas particles will be produced in order to fill up this extra space. So we're going to go back to our equilibrium equation. We have 2 moles of SO2 added with 1 mole of O2 produces 2 moles of SO3. As you can see here, our reactants, so that's our 2 moles of SO2 and our 1 mole of O2, the reactants have more gas particles, okay, 3 moles of gas particles, okay, so 2 moles of SO2, that's a gas, and 1 mole of O2, that's a gas. So there's 3 moles of gas particles on our reactants, and there's only 2 moles of gas particles on our products. So therefore, the equilibrium will shift in the direction to produce more gas particles. Therefore, in this case, the reactants will be favored. So some of the SO3 gas will react to form back into the reactants, so we'll go back to produce SO2 and O2. So equilibrium will favor the backwards reaction. So you can actually link the larger volume into decreased pressure as well, and you can link the decreasing pressure into equilibrium favoring the side with more gas particles. So in this case, when we have larger vessel, the volume of the vessel will increase. This means that the pressure will decrease. Pressure will decrease. So you can say equilibrium will shift in the direction. To produce more gas particles. So you can say that there are 3 moles of gas hence equilibrium will shift to favor the reactants. So you can say it favors the backwards reaction. So some sulfur trioxide gas, some sulfur trioxide SO3 gas will 2. Okay, so you can say that therefore the amount of SO2 is actually decreasing, okay? Because we want, so therefore the amount of SO3 is decreasing, sorry. The amount of SO3 is decreasing, so yeah. Okay, so that's because the backwards reaction is favored, okay? So we equilibrium is favoring the side of the more gas particles, so reactants have more gas particles, therefore the backwards reaction is favored. Some SO3 gas will turn back into SO2 and O2, therefore the amount of SO3 actually decreases. And that's all we need to write for this question, okay? So we need to link this one to, so we have to say increasing the volume will decrease the pressure, and the equilibrium will shift in the direction to increase the number of gas particles, so looking to increase the amount of gas particles. And we also have to say that the backwards reaction is favored, and therefore there will be a less SO3 gas produced. For question C, we need to say that for question C, so that's when we have the so explaining why when we remove the SO3 gas, more SO3 is produced. So you can say that when we remove SO3, the concentration of SO3 is decreasing. Hence, equilibrium will shift in a direction to replace some of the lost SO3 gas. Therefore, some reactants will turn into products. The forward reaction is favored. And if you link all those points together, so you're saying that the SO3 gas is the yield or the total amount of SO3 gas that the industrial plant produces will increase. Okay, if you can get a correct answer for both of these questions, you'll get an excellence grade. In terms of getting a merit grade, you need to have linking either the change of concentration or pressure to a direction. It's either the change in concentration or pressure to direction. Right, so it's either one. So basically, it's a bit, the marking is quite wordy, but it's just saying either one. So either you're linking the decrease of SO3, so you're producing more SO3, so that's possibly 1 point. So either one of these questions could get you a merit. To get an achieved, so it's just very generic. Achieved is basically just like your bullet points, like identify with the forward direction. So for this one, just identifying that the forward reaction is favored, therefore more SO3 is produced. And for question D, you're just saying, the decrease in pressure, so therefore some of the SO3 will turn back into SO2 and O2. So just basic bullet points will get you an achieved. Question E, when the reaction is carried out at 450 degrees Celsius, the Kc value is higher than the value at 600 degrees Celsius. Justify whether the oxidation of sulfur dioxide gas to sulfur trioxide gas is exothermic or endothermic. So in this case, we have decreased the temperature, which means that the heat energy will actually decreased, okay? So by decreasing the temperature, there's less heat energy, so therefore equilibrium will shift in the direction. So less heat energy. So equilibrium will shift in the direction so that more heat energy will be released in order to make up some of the lost heat energy. So there's less heat energy, so therefore equilibrium will shift in the direction to produce more heat energy or release more heat energy. Therefore, the exothermic reaction is favored because exothermic is the process of releasing heat to the surroundings. Endothermic is the process of absorbing heat from the surroundings. Okay, so in this case, equilibrium will favor the reaction that will release heat. So therefore, exothermic reaction will be favored. So we can say that justify whether the oxidation of sulfur dioxide gas to sulfur trioxide gas is exothermic or endothermic. So we see that the Kc value is higher, which means that because the Kc value is higher, that means that more products are being produced. So some of the reactants are turning into products, the concentration of the products are increasing, therefore our Kc value is becoming bigger, okay? So the difference between the concentration of the products and the concentration of reaction is more significant, therefore there will be more products than reactants. So these really two bullet points for this question. So first, we have to talk about how the exothermic reaction will be favored if we decrease the temperature. And secondly, you have to say that the equilibrium in this case will favor the forward reaction because there's more products being produced. And if you put these points together, you'll see that the forward reaction is actually the exothermic reaction because equilibrium is favoring the exothermic reaction and it's is favoring the forward reaction. So linking those two together, therefore the forward reaction, so the production of sulfur trioxide gas must be exothermic. Alright, so in terms of writing the answer, you can start with any one you want. You can start with writing about the Kc, or you can start by writing the temperature, so it doesn't really matter. So in this case, I'll just start off writing about the temperature, so you can say when the temperature decreases, when the temperature decreases, the amount of heat energy in the reaction decreases. Equilibrium will shift in the direction to reduce the change. In this case, as more heat in order to make up some of the lost heat. So to make up some of the, well, not really lost heat, but to make up the decrease in heat, probably is better. To make up the decrease in heat energy. So basically we're just saying that it's shifting in the direction to produce more heat. So shift in direction to produce more heat. Right, and now that's our first part. Okay, so we're saying that the equilibrium is favoring the exothermic reaction to release more heat, and now the second part we're saying that the Kc value is increased, therefore more products will be made, and therefore that will cause the Kc to increase. So you can say the Kc value so therefore the concentration of the product has increased, okay, meaning that the forward reaction must have been favored by equilibrium, meaning that the forward reaction is favored by equilibrium. Okay, so therefore the forward reaction is favored by equilibrium, and we know that equilibrium is also favoring the exothermic reaction, therefore we link that the forward reaction must be the exothermic reaction, and therefore the production of sulfur trioxide gas must be exothermic. So you can say that the forward reaction is favored by equilibrium, so that's more reactants, so reactants turning into products. And you can just conclude your statement, so therefore the production of SO3 gas must be exothermic. And that's really all we need to say for this question, okay? So in terms of marking schedule, you need to say when the temperature decreases, that means the amount of heat energy decreases, and the equilibrium will shift in the direction to produce more heat, will favor the exothermic reaction to make up some of the decrease in the heat. And that's our first part. Okay, that's our part number 1. Okay, our part number 2 is saying that when the Kc values increase, that means more products are being produced from the reactants. So there's less reactants and it's more products, meaning that some reactants have turned into products. So therefore, the forward reaction was favored, and therefore, because the equilibrium is favoring the exothermic reaction and is also favoring the forward reaction, therefore the forward reaction must be that exothermic reaction. So therefore, the production of SO3 gas must be exothermic. So linking all those points together, that will get you an excellence grade for this question. Okay, so in this case, to get a merit, so you're linking increase in Kc, links increase in Kc value at lower temperature to changes in the relative concentration of reactants or products. So basically you're saying that increasing the Kc means just higher concentration of products and lower concentration of reactants, and that will get you a merit grade actually. So just doing that will get you a merit. To get an achieved grade, if you just state that the decrease in temperature favors the exothermic reaction, so you're saying that because there's a decrease in heat energy, equilibrium will shift in the direction to produce more heat energy, and therefore it's going to favor the exothermic reaction. Just saying that will get you an achieved. To get an excellence, you need to link both of those points together. Okay. Alright, so therefore, that's it for that question. Okay, so question 3, the hydrogen sulfate ion HSO4- is an amphiprotic species because it can either act as an acid or a base. It can either donate a proton or it can accept a proton. So it can both accept or donate a proton, thus acting as an acid or a base. Complete the equations for the reaction of the hydrogen sulfate ion HSO4- with water in the box below. So HSO4, so the first one is HSO4- acting as an acid. An acid is a proton donor, which means that HSO4- will donate a proton to water. So what the products of this reaction will be SO4 2- because we're donating a proton. So SO4 2-, we're losing 1 H+, and water is going to accept the proton. So water is acting as the base. So we have plus H3O2 plus hydronium ions. For our second one, we have HSO4- acting as a base. So in this case, HSO4- is going to accept the proton from water, and water in this case is going to act as the acid because it's going to donate a proton to HSO4-. So the result is H2SO4 plus OH- ions. Right, question B. For grading for that question, probably just an achieve. Yeah, it's just an achieve level question. Okay, so just achieve if you can get up to here. Question B, the pH and relative electrical conductivity of aqueous solutions of potassium hydroxide and ammonia are shown in the table below, both have concentrations of 0.100 moles per liter. So we know that any hydroxide is a strong base and ammonia is a weak base, okay? So basically, the potassium hydroxide will undergo a full dissociation in water to become its ions. So in the solution, there's just going to be K+ ions and OH- ions. There's not going to be any KOH particles. So in terms of the ammonia is a weak base. It will not undergo a full dissociation in water, only undergoes partial dissociation to its ions. Therefore, it's also going to have some ammonium particles as well as some of its ions. So therefore, basically I'm just saying that KOH is a strong base and NH3 is a weak base. So as you can see here, the concentrations are both 0.100 moles per liter. However, the pH of KOH, the strong acid, is higher than the concentration of the weak base, NH3. So this means because pH is dependent on the concentration of hydronium ions and the concentration of hydronium. No, sorry. So it's depending on the concentration of hydronium ions and the hydroxide ions. So because KOH undergoes full dissociation, it's going to have more OH ions than NH3. Therefore, it's going to have a higher pH because it's going to be more OH minus ions than the hydronium ions. So we know electrical conductivity depends on free moving charged particles. Because there are more ions, because KOH undergoes full dissociation, there are more ions. Therefore, it's going to have a better electrical conductivity than NH3 because it's more free moving ions for the KOH. Alright, so for this question, okay, we can start off this question by saying that KOH is a strong base. Okay, and we need to define it, so meaning that it goes will undergo full dissociation. Okay, completely dissociate. That it will undergo full dissociation. Full dissociation in water to form its ions. Okay, so full dissociation, so that's K plus and OH minus. So we can actually say that therefore the concentration of KOH is equal to the concentration of OH minus ions because it's fully dissociates to its ions. So concentration of KOH is equal to the concentration of OH minus ions. Alright, so we can now link this one to NH3. So we say NH3 is a weak base, meaning that it undergoes partial dissociation. Okay, so meaning that it will undergo partial dissociation in water to its ions. So NH3 would be the so for NH3 it will be NH4 plus and OH minus. Alright, so you say it's only a partial dissociation. Okay, so therefore there are still NH3 particles in the solution as well as NH4 plus ions and OH minus ions. You can say therefore the concentration of ions produced by 0.1 mole per liter NH3 is less than the concentration of ions produced by KOH, so that's also 0.100 mole per liter. So that's a fair comparison. They're both of equal concentration. That's a fair comparison. So the amount of ions produced by NH3 is less than the number of ions produced by KOH. Okay, so KOH undergoes full dissociation to form its ions. Okay, so there are no KOH particles. It's just the K plus and OH minus ions. But for NH3, it only undergoes partial dissociation, meaning there's only going to be some NH4 plus ions and some OH minus ions, and there's also going to be some of the NH3 base that are still left. Okay. So in terms of the equations, it tells us to write the equations, to use relevant equations. So for KOH, we know that KOH that becomes, because this is a strong acid undergoes full dissociation, we'll use a reaction arrow. So we have our K plus ions plus our OH minus ions, okay? And if you want to add the states, you can to aqueous form. And in terms for our NH3, so NH3, that's an aqueous plus H2O in the liquid. Alright, so in this case, we're going to be using the equilibrium arrow because it doesn't go to completion. It's only a partial dissociation. Okay, so that's used to represent the equilibrium arrow is used to represent the partial dissociation. So we have, this will produce our NH4 plus ions as well as our OH minus ions. Yeah, so in this case, water acts as the acid and donates a proton to NH3, so we get NH4 plus and OH minus. So basically, the main point is that there's less ions when NH3 dissociates in water rather than when KOH dissociates in water, because KOH undergoes full dissociation, and NH3 only undergoes partial dissociation. So now we're going to link this to we're going to link this one to the electrical conductivity. So electrical conductivity depends on the amount or concentration, maybe a bit better, depends on the concentration of free moving charged particles in KOH. It fully dissociates to its ions. Of free moving ions, therefore a good electrical conductivity. Therefore, a good electrical conductivity. So you can say this is a strong base. So strong base. And you can say that NH3 is a poor conductor because it undergoes partial dissociation. Sorry, I can't spell. Okay. It undergoes partial dissociation to form its ions. Therefore, there are less free moving charged ions. Therefore, less free moving charged particles. Okay, so therefore, it's a poor conductor. Alright, so that's for the electrical conductivity, okay? For the difference in pH, okay, so basically, I don't really have enough space to write about the pH, but in this case, the main points you need to talk about is that KOH undergoes full dissociation to its ions. Therefore, there's going to be a higher concentration of OH minus ions produced rather than NH3. Because there's a higher amount of OH minus ions produced, because water is initially neutral, we have equal amount of hydronium and hydroxide ions. Because there's more OH minus ions produced when the KOH dissociates, therefore there's going to be a bigger difference between the concentration of OH minus ions and hydronium ions. Therefore, the pH is going to be bigger. For NH3, it's going to undergo partial dissociation. Okay, only some ions will be produced. The number of ions is less than KOH. Therefore, the difference between the hydronium ions and the OH minus ions is less than if it was KOH. Therefore, the pH will be less than the pH than KOH. Okay, so that's basically your main point for the pH. But in terms of your grades for this question, okay, so in order to get our excellence, so links conductivity and pH correctly to amount of relative concentration of ions. So basically just linking conductivity, you need free moving charged ions, which the dissociation of KOH produces more free moving charged ions, and dissociation of NH3 produces less free moving charged ions, and linking it correctly to the pH needs to be correct as well. So just saying, like I was just saying, the pH when KOH dissociates into its ions, more OH minus ions are produced, and when NH3 dissociates, less OH minus ions are produced. So basically just those two main ideas. Right, yeah, and that's really all we need to get an excellence. Okay, so in terms of getting a merit for this question, so we need to link the conductivity of each solution to the degree of dissociation. So basically, it looks like it's very wordy, but my opinion is probably just maybe just brief explanation. Maybe just either the conductivity or the pH. That should probably be enough to get you a merit. For achieved, once again, it's probably just bullet points, okay? So distinguishes the strong base from the weak base. So therefore, you're just saying the KOH is a strong base, NH3 is a weak base. That should get enough. That's an achieved point. You can get achieved for that one. So you can say that pH, like recognizes that pH is linked to the concentration of hydronium ions and OH minus ions. So just recognize that pH is depending on the hydronium ions and hydroxide ions. That's enough to get you an achieved. So achieved is basically just bullet pointers. Alright, so for question C, the table below gives the pH of solutions of ethanoic acid and nitric acid of concentration 0.200 moles per liter. Using the pH values to analyze the strength of the acids by calculating concentration of their hydronium ions. Alright, so in this case, okay, so we know that the concentration of hydronium is equal to 10 to the power of negative pH. So for CH3, COOH, we see that the concentration of H3 of hydronium is equal to 10 to the power of negative 2.73. So in this case, we should get this equals to 1.86 times 10 to the power of negative 3 mole per liter. For HNO3, nitric acid, that should be the strong acid. So this one is hydronium is equal to 10 to the power of negative 0.70. So 10 to the power of negative 0.70. That should give us 0.200 mole per liter. Alright, so as you can see here, we can see that the concentration of hydronium and HNO3 is equal to the concentration of, the concentration of HNO3 is equal to the concentration of hydronium, which means that it undergoes full dissociation to form its ions. Therefore, it's a strong acid because it undergoes full dissociation. As we see for the ethanoic acid, the concentration of H3O plus, which is the hydronium, is less than the concentration of the CH3COOH. So therefore, it's only undergoing partial dissociation, okay? Because it's undergoing partial dissociation, that means ethanoic acid must be a weak acid, and nitric acid must be the strong acid because it's undergoing full dissociation. So that's what we need to say for this question. So we can say that for HNO3, the concentration of hydronium, which is the concentration of hydronium ions is the same as the concentration of the acid meaning it undergoes full dissociation, meaning it undergoes full dissociation, producing more hydronium ions than CH and ethanoic acid. You can say for ethanoic acid, for CH3COOH, the concentration of hydronium ions is significantly less than the concentration of the ethanoic acid, then the concentration of the CH3OH acid, meaning it undergoes partial dissociation. So you can say that the ethanoic acid is a weak acid, and therefore HNO3 will be the strong acid. And that's really all we need for this question, okay? So we need a correct calculation for both of them. So that's 1.86 times 10 to the power negative 3 mole per liter concentration of hydronium for ethanoic acid, and 0.2 mole per liter concentration of H3O plus for nitric acid, okay? Alright, so that's correct calculation, and okay, so part 1 and part 2 are both linked. Okay, so we'll do part 2 first. So using your calculations in I above, predict the rate of reaction of each acid with a 2 cm strip of clean magnesium ribbon, Mg. So refer to the collision theory in your answer. Alright, so this is kind of a little bit like a rate of reaction question mixed with a acid-base reaction, okay? So we know that both acids are going to react with the Mg magnesium ribbon in an acid plus metal reaction, okay? However, we know that because the HNO3 strong acid completely dissociates into its ions, there's going to be a higher concentration of ions of it's going to have a higher concentration of H3O plus ions, okay? So that's the ions that's going to be reacting with the magnesium ribbon. However, for the ethanoic acid, it's only going to undergo partial dissociation, meaning that there's going to be less hydronium ions produced that's going to react with the magnesium ribbon. So therefore, we can link that to the concentration for the collision theory, okay? So we can say that both acids will react with Mg in an acid plus metal reaction. However, we can say that nitric acid is a strong acid, so nitric acid is a strong meaning there is a higher presence of hydronium ions, okay? And you can say for ethanoic acid, it undergoes partial dissociation. Therefore, so for ethanoic acid, it undergoes partial dissociation. Therefore, there is a lower concentration of hydronium ions. So therefore, there is a lower concentration of hydronium ions. So basically, you can say that the HNO3 will have a faster rate of reaction because there are more hydronium ions that can collide with the magnesium ribbon. Okay, so there's more effective collisions per second. So we can just really quickly write about the collision theory. So HNO3 will have a higher rate of reaction with Mg because there is a go to the next page hopefully this. Okay, so because there is a higher concentration of hydronium ions that are red with the Mg particles. Therefore, we don't really have to go for too much detail because this is the acid-base section. So we can just say, therefore, we can just directly link this to, therefore, there is a higher rate of reaction. And that's all we need for this question. Okay, so for an excellence, we need to explain that there's a higher hydronium concentration when nitric acid dissociates into its ions. There's a higher concentration of hydronium, and when ethanoic dissociates into its ions, has a lower concentration of hydronium. And you're going to link that there's a higher concentration of hydronium, therefore it's going to have a higher rate of reaction with the magnesium ribbon because there are more effective collisions per unit time. Okay, so more collisions. So we can just tag that one on. So more effective collisions, actually better. So more effective collisions per unit time. Alright, so and then we also need to say that so for E8 we need to link it to the more effective collisions per unit time for E8, and that's about it for E8. So E8 is saying there's more hydronium ions when HNO3 dissociates, so therefore it's going to have a higher rate of reaction. For a merit, okay, you need to link the so basically for a merit you can just do part C by itself. That will get you a merit. or you can do part II for a merit. So either part I or part II will get you a merit, but for excellence you need both to get an excellence. And for achieved, once again, it's just bullet points. Okay, so for achieved, it's just identifying weak or strong acids that could be achieved. One correct calculation, that's an achieved, and you can say, oh, the strong acid will react faster because that's a faster rate of reaction, that will get you an achieved. So basically, once again, for achieved, it's just bullet points, okay, bullet pointers, and that's enough to get you achieved. Alright, so thank you for watching this video. I hope you enjoyed, and I hope to see you on the next one.